All right, so we're going to start in on chapter 19, talking about aldehydes and ketones. Okay, these are sort of functional groups that we've introduced before. We talked last chapter about how to convert alcohols into aldehydes and ketones, but we've never really talked exclusively about these functional groups. So that's what we're going to do here today. All right, so just to remind us, aldehydes and ketones, these are both carbonyl-containing compounds. And you may or will hear me gripe about the fact that they're considered different functional groups because they have very similar to behavior. An aldehyde is when you have this terminal carbonyl group, meaning it's on the end of the molecule. A ketone is when you have that carbonyl group on an internal carbon. So not sticking out off of the end, but somewhere in the middle. So aldehydes are terminal carbonyl groups. Ketones are internal carbonyl groups. Okay. One thing to note about a aldehyde in particular, because, right, carbon likes to have how many bonds? 4. So this carbonyl carbon right here has a hydrogen that's sticking off of it. Sometimes you'll see that hydrogen explicitly drawn. Sometimes you won't, right? You don't have to. It's a good idea to remember that it's always there, that there's that 4th bond that we're not looking at. Okay? Importantly, one thing we want to note about this hydrogen, because I think it's natural to be like, oh, different functional groups. Maybe that hydrogen is the reason why they're different. No. This hydrogen is very much so not acidic at all. It is very hard to remove that hydrogen. That is not going to be a common feature of aldehyde reactions, is that this hydrogen somehow gets donated. That's not what happens, all right? So we just want to make a note. That is not a donatable hydrogen. That is not an acidic hydrogen. All right? Okay, so 2 main uses for aldehydes and ketones in the lab. One of which is arguably not even arguably, objectively the most commonly used organic compound that we use in this lab, which is what? Acetone, absolutely. So aldehydes and ketones, one big feature of aldehydes and ketones in the lab is as a solvent. Okay, so if we look on our polarity spectrum here, nonpolar to polar, all right, let's put down a few molecules that all have similar molecular weights here and see if we can rank these from polar to nonpolar. All right, we have an alcohol, an alkane, and a ketone here. And I want you to rank them from non-polar to polar. Which one is the least polar? Which one's the most polar? All right, so which one's the least polar? The alcohol, the alkane, or the ketone? The alkane, right? So alkanes are going to be the most nonpolar. Remember, we talked about how this is a result of these intermolecular interactions. These ones only have these very weak dispersion forces available. All right, so then on the flip side, which one is the most polar molecule up here? It's going to be the alcohol. Okay, the alcohol is the most polar because that OH group is capable of hydrogen bonding. the strongest type of intermolecular interaction. Okay, a ketone, because we've replaced that hydrogen with a now carbon-oxygen double bond, a second bond there, a pi bond, we've lost the ability to hydrogen bond. Nonetheless, this is still a polar functional group. It's got a partial negative charge on the oxygen, a partial positive charge on the carbon. It's just that those interactions aren't as strong as hydrogen bonding interactions. They're what we call dipole-dipole interactions. Okay, so because of it, our acetone sits slightly more on the non-polar end. I'm not going to put it all the way in the middle because truthfully, it is still a polar functional group. So I'm going to put it right here. All right, but nonetheless, it would be considered a functional group of intermittent polarity. All right, and that's why we use it so often in the lab, is because it's good at dissolving these non-polar organic compounds that are stuck to our glassware. But then we can also rinse it down the drain because it mixes with water, this polar substance, right? So it's a good solvent of intermediate polarity. Okay, so we can just make note. Ketones and aldehydes. Good solvents, intermediate polarity. Oops. Okay, we will talk about the other big use of aldehydes and ketones in the lab, although I've kind of sort of hinted at it here. It's that this carbon has this partial positive charge, making that carbon a good what in a chemical reaction? Electrophile, electrophilic, carbonyl carbon. We're going to have that memorized by the end of this chapter, all right? Because that's going to be a very common feature that we see in our reactions over and over and over again. All right, we're going to save our reactions here till the end. We want to jump to the next thing, which is always how we sort of introduce our functional groups, and that is nomenclature. Okay. We can just note that both aldehydes and ketones are considered in our nomenclature functional groups with priority. Right, we'd introduced a few last time, the ether and the epoxide that were considered substituents, so they didn't have this concept of priority attached to them. Aldehydes and ketones both are considered functional groups with priority. All right, let's start with ketones. All right, we'll use this example molecule right here. Step one is we're going to find our parent chain. Okay, and for ketones, again, we consider these functional groups, so we're going to update the suffix on the end of our parent chain. Ketones have the suffix -one, O-N-E. All right, I'm going to do the aldehyde notes here as well, so I'm going to leave a little space. The next step is to find the substituents. There's nothing special there. The next thing we're going to do is number our parent chain. And again, that ketone functional group has priority. And then I'm just going to put the name together, and there's nothing really special about that. Assemble, no, assemble that name. Okay, so for this one here, again, find our parent chain, our 1, 2, 3, 4, 5 carbons. Okay, We're going to number that parent chain 1, 2, 3, giving that ketone functional group, our carbonyl, the lowest number. So this would be 3-pentanone. Right, if it was an alcohol group, it would be pentanol. Instead, we're going to put that O-N-E ending on there, pentanone. All right, so everybody take a second and name these 3 ketones for me here. All right, so we're going to find our parent chain. 1, 2, 3, 4, 5, 6 carbons here. We're going to number our parent chain, and we're going to number it in such a way where the only thing we're paying attention to is making sure that that carbonyl group gets the lowest possible number. I don't care about the chlorine. So I'm going to number this direction here. 1, 2, 3, 4, 5, 6. I'm going to assemble my name. My chloro group is on carbon 6, so 6-chloro. And then 2-hexanone. All right, so this one's actually slightly deceptively tricky here, okay? I have a feeling that most of you said that this compound here was 2-butanone. All right, it turns out that you should not include the 2. This molecule here is just butanone. All right, so let's think about why that is real quick. If I move this carbonyl group over here, is this 3-butanone? No, right? Because all we would do is change our numbering scheme and number from left to right instead of right to left. All right? What if I moved it over here? Would this be 1-butanone? Right, exactly. It's not a ketone anymore. It would become an aldehyde. So, in this case, the unambiguous way to name this group, there is only 1-butanone, and it is 2-butanone. But this is the only butanone that you could possibly draw, right? And in that case, we don't include our number. Usually after 1 or 2 carbons, we lose that sort of ambiguity. We wouldn't say 1 chloromethane, we'd just say chloromethane. But as soon as you get to be more and more carbons, that goes away. Ketones, because of the definition of a ketone, you got to remember, this is going to be the largest one that you don't have to put the number on. All right, so now this one, importantly, in our previous compounds here, we had hexanone and butanone, and that AN implied that there were all single carbon-carbon single bonds in that molecule. Now we have this carbon-carbon double bond here. So it's going to be an enone. We got to again find our parent chain. 1, 2, 3, 4, 5, 6, 7. We're going to number our parent chain to prioritize that carbonyl group. 1, 2, 3, 4, 5, 6, 7. Okay, but now I got to indicate the position of both the ketone group and the double bond. So this would be hept 5-ene 3-one, where now we have the ene in the name to indicate the position, or to indicate the presence of that double bond. Okay, so now let's move on to aldehydes. Aldehydes are going to have a different suffix associated with them. So let's just do a sample aldehyde here. We can even... All right, so for aldehydes, instead of using the suffix "-one", we're going to use the suffix "-al", A-L. All right, nothing special about our substituents. We're going to remind ourselves that aldehydes are a functional group that has priority. So if that aldehyde functional group has priority, what carbon is that aldehyde group going to be on in my molecule? Number 1. Does it matter how big or small the chain is for that aldehyde group? No, if that has priority, we're always going to pay attention to that and give it the lowest number. Because of the definition of an aldehyde and the fact that it has to go on the end of a molecule, aldehydes are functional groups with priority, and they will always be carbon 1. So because of that, when we name our molecule, this is 4 carbons, this would be a butanal. We do not include the locant in the name. There's no such thing as a 2-butanal or a 3-butanal. Necessarily, it's going to be on that first carbon. So we don't have to say 1-butanal, 1-pentanal all the time. It's just implied that it's on carbon 1. Okay? So under our numbering here, we're going to say it has a priority. It's always going to be on carbon 1. And when we assemble our name for aldehydes, we do not include the locant of that functional group. We can just say the carbonyl. Okay, so again, this wouldn't be 1-butanal. It's implied that it's on carbon 1, so just butanal. All right, so then everybody take a second and name these 3 aldehydes for me. so let's do this first one here. Find our parent chain. That aldehyde group is always going to be on carbon 1, so that fluoro group is on carbon 3, 3-fluoro propanal. All right, this next one, finding our parent chain. 1, 2, 3, 4, 5, 6. We need the longest continuous set of carbons. So 1, 2, 3, 4, 5, 6. That methyl group is on carbon 4. So 4-methyl. Again, the 1 for the aldehyde group is implied, so this is just hexanal. All right, and then lastly, again, the AN in these names had implied that they were all carbon-carbon single bonds. If we have this carbon-carbon double bond, we're going to have to include an EN at the end. Our longest continuous set of carbons, 1, 2, 3, 4, 5. If we figure out where that double bond is located, it's between carbons 4 and 5. Since there's only the one number, I can put it out front, 4 pentenal, but you could also build it into the name pent-4-enal. But importantly, the name includes now the EN to indicate the presence of that double bond. All right, so last time we had talked, when we introduced thiols, we had talked about what happens when you have a molecule that has multiple functional groups, each with priority in the name. And we took a look at at this chart right here, okay? Ranking this priority list of our functional groups, ranking them from lowest to highest priority here. The lowest end, we have our alkynes and our alkenes. And then we talked about how thiols were lower on the priority list than alcohols. So remember, if a molecule had both an alcohol and a thiol in it, the higher priority group, the alcohol, gets referred to by its suffix, and the lower priority group gets referred to by its prefix. It becomes a substituent. All right? So now we're going to update this list with the two new functional groups. Okay? They are both higher priority than anything else we've studied. After alcohols comes ketones, and the highest priority at this point are now the aldehydes. All right, we already talked about the suffix for these two functional groups, right? The suffix for the aldehyde is that Al, and the suffix for the ketone is the one, O-N-E. All right, but the prefix for these two functional groups is actually the same. It's oxo. Okay. So let's do this first one together here, and then I'll have you do the other two on your own. We're going to look at this molecule here. 1, 2, 3, 4, 5 carbons in my parent chain. But it's got two functional groups in there. It's got a ketone, and it's got an alcohol. When I look on my priority list, alcohols are lower priority than ketones. So that means this alcohol group, it loses its functional group status, and it becomes just a substituent, what's called the hydroxy substituent. So when I number my chain, I'm going to pay attention to only the position of that ketone group because it's the highest priority group. So this molecule here would be 4-hydroxy 2-pentanone. Okay, so take a second and complete these other two molecules for me. All right. So we're going to find our parent chain. 1, 2, 3, 4, 5. The thiol group, right? We got two functional groups, a thiol and an aldehyde. The thiol is the lower of the priority groups, so it becomes a substituent and gets the mercapto name. Let me make a tiny bit more room. So when I number my parent chain, I'm going to number from that highest priority aldehyde group. So this becomes 3-mercapto pentanal. All right, and then this molecule here, my parent chain, 1, 2, 3, 4, 5, 6, 7 carbons. This one also has two functional groups, a ketone and an aldehyde. The ketone is the lower of the two priority groups, right? Aldehydes beat ketones according to our list. So this is now a substituent on that parent chain, what's referred to as an oxo group. I'm going to number from the highest priority group. So this would be 5-oxo heptanal. Okay, so we updated our priority list, to include ketones and aldehydes. They are going to sit at the tippy top of our priority list. Aldehydes are now the highest priority functional group we know. Ketones are right below that. And if they have the suffix, they actually share the suffix oxo, should they be the lower priority in the molecule.
If you had another aldehyde on the end, it would just be 5-oxo dipentanal?
Heptadiol. Heptane diol, right? Because it'd be the D and the N next to each other. Yeah, I mean, that's not a bad example here. So this one here, let's just do a smaller one, 3 carbons. Okay, so this would be propane diol. And you still don't have to include the number of the other group because it's implied it's on the other end of the molecule. If you had 3 aldehyde groups in there, all of a sudden all bets are off and there's a more complicated nomenclature scheme for that. We're not going to cover all that crap. There's a carbaldehyde thing you have to throw in there. I'm not going to even pretend to actually really fully understand it. Okay, now last thing, there are 2 special aldehydes and ketones that we just got to know, actually one of each. All right, the first one we actually just, we've discussed quite a bit here. The most commonly used one in the lab is acetone. Okay, importantly, this thing is acetone would not be its IUPAC name, right? Or at least not the name you would get according to the IUPAC rules. This would be propanone. All right, but absolutely nobody, including the IUPAC, calls it propanone. They've admitted defeat. The common name has been 100% accepted as the name of this molecule. This molecule right here is acetone. All right, and then the other one is an aldehyde, the smallest aldehyde that you could possibly have, just one single carbon. Right, which according to our rules we would call methanol. All right, but again, nobody calls it methanol. The IUPAC accepted name would be the common name. Does anybody know what this molecule is? Yeah, this is formaldehyde. All right, you might know formaldehyde from biology class if you ever did any sort of dissections. This is a chemical that's used to preserve dead bodies. Both of these are just ridiculously widely used in the industrial chemical industry. I'm talking like tens of millions of tons of this stuff is produced every year to be used out in the industry. So anyway, it's just their common name has stuck around, and that's what we call them. All right, so these are 2 special ones that don't follow our IUPAC rules, and we just got to know. Acetone, the smallest ketone that you could get, and formaldehyde, the smallest aldehyde that you could get. Okay, let's talk about how we prepare aldehydes and ketones. Preparation. All right, we have a few different methods for preparing aldehydes and ketones, one of which was first introduced just in this past unit and is the most common way for generating aldehydes and ketones, at least in the laboratory, and that would be if we started with, for example, a secondary alcohol, we could convert that to a ketone. And if we started out with instead of primary alcohol, we could convert that to an aldehyde. All right, and again, these were reactions that we discussed last chapter. What type of reaction is this? Absolutely. So First way we can prepare aldehydes and ketones, and again, a very common way of doing it in like a chemistry lab would be oxidation of alcohols. Okay. For a secondary alcohol, remember that it can only be oxidized to a ketone and then it's stuck. It can't be further oxidized. So for these, you could either use a strong oxidizer, those chromium-containing compounds, or you could use a weak oxidizer, the old school PCC, or that new aged Des-Martin periodine DMP. Either one of those choices, any one of those choices rather, would allow you to convert a secondary alcohol to a ketone. Okay? If we started out instead with a primary alcohol, we got to be careful. And which one of our categories would we pick if we wanted an aldehyde? Yeah, only the weak oxidizers would work, either the PCC or the DMP, right? If we used a strong oxidizer, we would instead get a carboxylic acid. Okay, so these are methods of oxidizing alcohols. This is our first way of preparing aldehydes and ketones. All right. Another way is one that we discussed last semester but haven't yet discussed again this semester, so let's just remind ourselves. This is what's called an ozonolysis reaction. All right, and this is where we start with an alkene and we treat it with ozone, O3. All right, that's where the name ozonolysis comes from. These are what we would call oxidative cleavage reactions. All right, and as the name implies here, what this reaction does is it takes this alkene and it is going to cleave that double bond, hiya, right down the middle, breaking this molecule into two smaller fragments. All right, but it's an oxidative cleavage. On either end is now an oxygen. Right, so this molecule got broken into these two distinct fragments here. In this case, they're identical. Depending on your alkene, that may not be the case. Okay, one last method here is going to use kind of like a modified version of a reagent we already covered. So let's kind of just remind ourselves, all right, one of the reactions of aldehydes and ketones that we discussed last chapter is if we take a ketone and we treat it with something like lithium aluminum hydride. Okay, what's our product that we get? An alcohol. So this would be the opposite of an oxidation reaction, what's called a reduction reaction. All right, so this would be if we started out with a ketone, we get an alcohol. All right, it turns out that if you started out with another carbonyl containing functional group, but one that's a little different, one that we've haven't yet talked about in lecture, but we've seen a few times, an ester. all right, especially in the lab. If we treat it with that same reducing agent, what happens is we actually would get the same alcohol. Oh no, I'm sorry. We would get an alcohol, all right, and it would actually cleave off that ester functional group. So the alcohol that I get at the end are just these 3 carbons from my ester. All right? Not only does it reduce that functional group, that carbonyl group, it also breaks that carbon-oxygen single bond. Right? So that carbon originally had 3 oxygens on it, and it's going to fully reduce it to having only 1. Okay? So we didn't really talk about this when we introduced this lithium aluminum hydride, but because of this here, we can consider this a strong reducing agent. Right? We talked about strong and weak oxidizers. Now we're talking about strong and weak reducers. Lithium aluminum hydride would be a strong reducing agent. Right? Can fully reduce that ester. Okay. So now we're going to introduce a sort of derivative of this lithium aluminum hydride, what's called dibutyl aluminum hydride, or DIBAH, DIBA. That's how you're going to see it on your reagent list, is abbreviated like that. Okay, so DIBA is an aluminum hydride. It's got that hydrogen on it, but now it's got these 2 big butyl groups sticking off of it. All right, and those big bulky butyl groups, they make this a weak reducing agent. So if I started out with that same ester, and instead of hitting it with that strong reducing agent, I hit it with this weak reducing agent, the DIBA. All right, it will reduce it once by cleaving off that oxygen. All right, but it doesn't reduce that carbonyl group, so instead I get an aldehyde. Okay, cool. All right, so we have these 3 reactions, or at least 3 categories of reactions. One of which we actually discussed just last chapter, these oxidation of alcohols. We also talked about this ozonolysis reaction. That's sort of a review of last semester. And now we got this new one here, this DIBA, which is a weak reducing agent. It would convert an ester into an aldehyde. Okay. All right, so now the next topic that we're going to discuss is the reactions of aldehydes and ketones, and specifically what we would call nucleophilic addition reactions. right? So in these reactions, our aldehyde or ketone is going to be playing the role of an electrophile. We're going to take some nucleophile and react it with our aldehyde or ketone. Okay, so let's take a second and talk about aldehydes and ketones as electrophiles. All right, there are two main features that makes this molecule such a good electrophile. The one of which we talked about at the beginning, it's this polar bond where carbon is bound to the more electronegative oxygen. So oxygen is pulling electron density onto itself away from that carbon atom. Right, we have this polar bond here that leaves this carbon relatively electron poor. All right, but the other important feature of these aldehydes and ketones, of these carbonyl groups that makes that carbonyl carbon such a good electrophile is it has this, and I'm going to say quote unquote, leaving group. This this pi bonding pair of electrons here that should that carbon get attacked can move and result in not breaking carbon's octet rule. Right, so this pi bond, what we're going to see over and over again, this pi bond plays the role of a, quote, leaving group, right, which prevents carbon from having too many bonds should that carbonyl group get attacked by a nucleophile. So these are two important features, one being relatively electron deficient, as well as having this good leaving group so you're not breaking your octet rule. Okay? All right, we talked last unit when we were talking about epoxides. We sort of took the world of nucleophiles and divided them into two bins. We have our basic nucleophiles and our acidic nucleophiles. Basic nucleophiles are nucleophiles that you would see under basic conditions, and acidic nucleophiles are nucleophiles that you would see under acidic conditions. All right? Our basic nucleophiles are kind of our traditional good nucleophiles, right? They have this net negative charge. Okay? Because remember, under basic conditions, we should not see any positive charges, right? So no positive charges under basic conditions. Okay? Our acidic nucleophiles, remember a nucleophile by definition still has to be electron rich. So it's not like these are going to be positively charged. But what we do see in this category are our neutral nucleophiles. Okay, with the exception of these halogens, because they're such poor bases. Remember, they're kind of the oddity that can exist under acidic conditions, even with that net negative charge. Because remember, we'd said under acidic conditions, we should have no negative charges. And then we made that exception for the halogens. Okay. So our acidic nucleophiles, we have our halogens as well as our neutral compounds. So our oxygen with its lone pair can still be a nucleophile in water. Our oxygen with its lone pair can be a nucleophile in, for example, an alcohol. Same thing with sulfur. Sulfur is a good nucleophile even when it's neutral. We can have that under acidic conditions. All right. Before we move on here, there's one element that's kind of like conspicuously missing here. All right. If we look on our periodic table, we have some carbon nucleophiles. And then we don't have any nitrogen nucleophiles, but we do have oxygen nucleophiles and halogen nucleophiles. All right, we're going to specifically omit nitrogen from this list because it turns out that nitrogen is going to be more helpful to think about in its own special little category. It has kind of weird reactions with aldehydes and ketones, right? The rest of these nucleophiles we can kind of throw together, and their reactions of aldehydes and ketones follow the exact same pattern. Nitrogen we're going to see is a little bit different of a beast. So we're going to omit any nitrogen nucleophiles from this list, and we'll talk about that next week as to how those reactions are a little bit different. Okay. One more thing that we can add here. What's another really good carbon nucleophile under basic conditions? What's up? No. So a carbon nucleophile. So I'm looking for a nucleophile that would create new carbon-carbon bonds. A Grignard, absolutely. So a Grignard, even though it doesn't have that net negative charge, like a lot of these other basic conditions, right? In a Grignard reagent, all of that negative charge is sitting on that carbon atom. Grignards are a strong base. This is another example of a nucleophile that we need to put in the basic category here. Okay, so under this basic category, we have all these great nucleophiles, things that we think of as great nucleophiles. They have these net negative charges, so of course they're going to be good nucleophiles. Under acidic conditions here, we have these neutral nucleophiles, all right? And a lot of these would be considered to be weak nucleophiles. So for example, water and alcohol, these are not great nucleophiles. They would be classified as weak nucleophiles. All right, so then how can we still get away with these reactions and using these nucleophiles? Okay, so under acidic conditions, what we would see is that carbonyl group gets protonated. Rather, the carbonyl oxygen gets protonated in those reactions. Okay, so under acidic conditions, if we're going to take a look at the electrophile in those reactions, it's actually not our carbonyl group. It is a protonated carbonyl group. All right, so this would be our electrophile under basic conditions. Under acidic conditions, our electrophile is now that protonated carbonyl group. Okay, and remember these two features that makes this carbon such a good such a good electrophile is not only that it has this partial positive charge, but that lone pair is being pulled up onto that oxygen. And since that oxygen with a protonated carbonyl group has a positive charge, it's going to be pulling that electron density onto itself even more strongly, right? That lone pair is going to be pulled onto that oxygen very easily. So while we would consider an aldehyde or ketone to be a good electrophile, when we protonate it, all of a sudden it becomes just an absolutely fantastic electrophile, a great electrophile. Okay, that positive charge on that oxygen is only going to serve to pull more electron density away from that carbon atom. All right, so that's why under acidic conditions we can get away with using these weak nucleophiles, because we've just, yeah, we have a weak nucleophile, but we have a really fantastic electrophile, so it kind of makes up for it. Okay, great. All right, so now let's take one of our nucleophiles and react it with our electrophile, our ketone, or aldehyde. All right, so first we're going to do one of our basic nucleophiles. For the sake of simplicity, we're just going to stick with our acetone here. We're going to use one of our nucleophiles, our basic nucleophiles. Let's go ahead and use the cyanide ion. All right, and I want you to take a second and see if you can give me the full reaction mechanism here for this reaction between acetone and cyanide.
I didn't get that. Could you try again? Shh.
All right, so natural first step, let's have our nucleophile attack our electrophile. Again, what's going to make this carbonyl such a good electrophile is it can bounce that pair of electrons up onto that oxygen. All right. Okay, and remember, we had a special name for these intermediates here because of their geometry. This is what we called the tetrahedral intermediate. That carbonyl group, because of those 3 electron regions, is a trigonal planar geometry. When you add that 4th bond, all of a sudden it becomes a tetrahedral geometry. And so again, we got the special name for this intermediates. This is the tetrahedral intermediate. All right, and now I'm going to add my nucleophile. I got that new carbon-carbon bond. Okay, so at this point, we have this alkoxide ion. How this reaction would proceed is really you would use a mix of both the cyanide ion and the protonated version, hydrogen cyanide. Okay, and so then the last step would be protonating that formerly carbonyl oxygen, giving you an alcohol. And just note that using the protonated form of your nucleophile is just a clever trick, because what's going to be produced? Your nucleophile, right? As soon as that oxygen removes that hydrogen, now you've just replenished your supply of nucleophile. So this thing can turn right back around and react with a new molecule of acetone. Okay? So under basic conditions, our first step here was the nucleophilic attack. And then we did a proton transfer step. Our nucleophilic attack generated this negatively charged alkoxide ion. But that's okay, because this was under basic conditions. All right, so now let's take a different nucleophile. And this time we're going to react under acidic conditions. Okay, and we'll react with one of our nucleophiles that we can use under acidic conditions here. And again, I want you to come up with the reaction mechanism for this reaction. All right, so if under acidic conditions, we try to do the same first step. We tried to have our same nucleophilic attack and create that tetrahedral intermediate. All right, we have a problem with this intermediate. What is that? That negative charge, right? So under acidic conditions, we said no strong bases, which meant AKA no negative charges. All right, so that can't be the first step. And we had sort of talked about this with your electrophile under acidic conditions. Instead, what is the first step going to be in this reaction? Protonation. All right. So when in doubt, if there isn't like an acid catalyst or something that's been provided, under acidic conditions, your default for your proton donor is going to be the hydronium ion. Okay, and then your default proton acceptor is going to be water. Right? It can't be that strong base hydroxide. That would break our rule about no strong bases. Okay. So, first step I have to do is use that hydronium ion and protonate that carbonyl oxygen. Now, when my nucleophile attacks and I form my tetrahedral intermediate, it does not have any negative charges. No strong bases in this tetrahedral intermediate. Okay. However, because my nucleophile started out as neutral, when it does its attacking, it's going to have a formal charge of +1. So our last step, and we're going to kind of see this a lot, our acidic mechanisms usually have 1 or 2 extra proton transfer steps. So in this case, we got 1 more proton transfer step to get to our product. And again, our proton acceptor, we're going to say is water. Right, our base is water. Okay? So in both cases, you're attaching your nucleophile to what was formerly your carbonyl carbon. All right, your oxygen, your carbonyl oxygen is becoming an alcohol group. Okay, we just have our differences between our acidic and our basic conditions that we've discussed. All right, basic conditions, we can kind of make a note. Right, the opposite, no strong acids, aka no positive charges. All right, but again, in both cases, we have our nucleophile attached to our formerly carbonyl carbon. All right, so if we think about it, that means that if we took, for example, acetone, and we treated it with a strong nucleophile under basic conditions, the hydroxide ion, we would get that OH group from our carbonyl oxygen, and then our nucleophile, which is also a hydroxyl group. So you have these 2 OH groups attached to the same carbon. This is what's called a hydrate or a gem diol. I have no idea where that comes from. I have a feeling gem is Latin or something. What?
Like Gemini, like twin?
Okay, sure. Boom. There we go. All right, great. Yeah, so Latin or something then?
Yeah.
Yeah, okay, cool. All right. If we did instead reacted this under acidic conditions, but used that weak nucleophile water, and again under acidic conditions, so we have these hydronium ions, we would get the exact same product. Okay, we would just have different mechanisms, right? So our order in which we did our protonation steps versus our proton transfer steps versus our nucleophilic attack steps would be different, all right? And you're gonna work out as one of your homework problems these two mechanisms. But we can just note that in both cases you're attaching the same thing to that carbonyl carbon, so you're gonna get the same product. Okay? One note about these gem diols here. Anytime you have an aldehyde or ketone in the presence of water in an aqueous solution, you always have this equilibrium that's formed between the aldehyde or ketone and that gem diol. But for just about every aldehyde or ketone, this equilibrium dramatically favors the ketone or aldehyde. So our ketone gem diol equilibrium favors that ketone. There's one big exception here, and that is the teeniest, tiniest of all of these, formaldehyde. Formaldehyde will be almost completely converted to its gem diol under in the presence of an aqueous solution. Cool. All right, we're gonna pick up with this particular chapter next week. More about aldehydes and ketones.